Hello dear friends. In the previous video lecture we started talking about the improvement algorithms for layout design. We have seen the general procedure for these improvement algorithms, and we also talked about a simple pairwise exchange method. In this video lecture we will talk about more on improvement algorithms, and we will learn the Kraft and MCCraft algorithms. So let's get started. Kraft is one of the earliest algorithms in layout planning. It stands for Computerized Relative Allocation of Facilities Technique. So Kraft is the shorthand notation for this word. Kraft uses the from-to chart as input data for the flow and uses distance-based objective function to compare alternative layouts with each other. And remember, in distance-based objective function, we multiply the flow between department I and J with the distance between I and J and cost of transporting one unit from I to J, and we add the summation of this multiplication over all departments I and J. Okay, so this is the distance-based scoring that Kraft uses. Kraft is an improvement algorithm. It means that it starts with an initial layout and tries to improve it. The layout is represented with unit square areas, and to the computer it's given as a matrix of numbers. The distance is measured in terms of rectilinear distance, and the distance between the departments are measured from centroid of one department to the centroid of the other department. It means that you first need to find the centroid of the departments and then calculate the distance between them using the rectilinear distance. In Kraft, the departments are not restricted to rectangular shapes. They can have any shapes, in fact. But of course, they need to satisfy the contiguity and connectedness rules to be feasible. And in order to improve a department or a layout, exchange of departments are considered. Since the layout is given to the computer for Kraft as a matrix, it must have a rectangular shape. Okay? But it doesn't mean that your final layout should be rectangular. In Kraft, you can use the so-called fixed departments. It means that you have a department and you can fix its place, its location. And Kraft never tries to exchange these departments. So if you want to have a different shape than the rectangular one, you can use a number of dummy departments with by giving zero flows with these departments, artificial flows with these departments, and you can fix their positions so that you can establish layouts other than the rectangular shapes, or inside your layout you may have different building irregularities. For example, if you have an elevator space, assume that you have such a rectangular shape for your layout, but assume that there is an elevator already designed to be here. So what you can do is you can define this field as a department, as a dummy department, and you can fix its position so that whenever Kraft tries to make exchange, it never touches this fixed department. So in your final layout, this elevator place will be exactly here. And it's possible to do this in Kraft. Okay, so you can also consider this option to decide or to determine the location for the aisles, stairways, and etc. Or also you can use this option to create departments with different shapes other than rectangular ones. Basic steps of the Kraft algorithm are as follows. First thing is to determine the centroids of the departments. If the department shape is weird, then calculating the centroid may also be difficult a little bit. But if it's rectangular, then it's straightforward. Then, when you have the centroids of all departments, we can calculate the rectilinear distance between these centroids easily. Okay. Then we calculate the objective function value of the current layout or the initial layout. And then, like in the pairwise exchange method, we consider the exchange options between the departments. But here, in pairwise exchange, you can only exchange departments, or we assume that all departments have the same size. But here in Kraft, you don't need to have this. Either you can exchange two departments which have the same size, or you can exchange departments that share a common boundary. Okay. Then what do you do when you choose two such departments? You first estimate the change in the objective function value with this exchange. And in order to make this estimation, you assume that the centroids of the departments will be fixed. We will talk on this a little bit more in detail, but assume that you are replacing department A and B, and in their current shape, department A centroid is in an XY coordinate, and department B's coordinate centroid is in another XY coordinate. When you replace them, the centroid of B will not be the centroid of A because their sizes will be different. But we assume that their centroids are switched, so that the new centroid of B becomes the old centroid of A, and new centroid of A becomes the old centroid of B. So this is the estimation. As I said, we will talk on this a little bit more. So we estimate the change in the objective function value. Then, since there are alternative such exchanges, you need to calculate all estimated changes and select the greatest one. So this is the so-called steepest descent type algorithm, or a greedy algorithm. Then we repeat this procedure of exchanging departments until there are no further reduction in the objective function value. So these are the steps, basic steps of the Kraft algorithm. Okay, then how do we determine the estimated change of two departments, exchanging two departments? Let's assume that we have this department, okay, A, and another department sharing some common boundary with this one, which is department B, which is a larger one. Okay, so let's assume that this is department I and this is department J. Okay, and so the centroid of the first department, when you calculate it, it should be somewhere around here. Okay, you need to calculate exact centroid. And the centroid of department B, let's assume that is somewhere around here. Okay. Now, when we exchange these departments, what will happen is department J will move to this part and department I will move to that part. And maybe the new shape of these departments would be something like this. So this part will be department B, but maybe it's longer because it was larger. Okay, so let's assume that this part is department B, and department A will have this side. Okay, now I and J I replaced, so this part is I now and this part is J. And if you look at the exact centroids of these two shapes, the centroid of this I is here and centroid of J is somewhere around here. Okay, you see the old centroid of I, which is this one, is not equal to the centroid of J. Their centroids are changed. But what Kraft does in order to estimate this is it assumes that the new centroid is the same, like this one. And it also assumes that the centroid of this eye is this one. Okay, so it uses the old centroids but switches it instead of using the exact centroids. So this is some kind of an estimation, and depending on how well this estimation is, in fact the actual cost can be overestimated or underestimated. Okay? And the error that we are making with this estimation depends on the sizes of the two departments, their relative size of the departments with respect to each other. If one department is very small and the other one is very large, and then the estimation error would be larger. But if the department sizes are closer to each other, then the error will be smaller. So after this estimation, when you make this exchange, then the correct centroids should be calculated after the exchange. Then when you decide to exchange two departments, since they provide the greatest improvement in the objective function, how do we exchange these two departments? If the areas of the two departments are equal, it's easy. One takes the place of the other, takes the shape of the other one. Okay? If the sizes are equal, it's very easy. But if the areas are not identical, then what do? We first draw a box enclosing two departments, okay, and remove the departments from its box. So if let's assume that we have such a department, the first department, and there's another department, let's say sharing some boundary with this one in this shape, and let's assume that we are going to exchange these two. Okay, so what do is first we draw a box enclosing the border of these two departments. Okay, so this is the border of these two departments. Then we delete or remove the departments from this box. Then we select the smaller department. Let this department be K. The number of departments that this smaller one requires is K. Assume that this is the smaller one. This is the smaller one. Okay. So then what do? You count K grids from the non-adjacent side of the larger department. Okay, this is the larger department, and this side is the adjacent side. This side is the non-adjacent side. Okay, it says that count K grids from the non-adjacent side of the larger department by swiping down, starting from the leftmost upper corner. Okay, so this is written if for the case that the smallest department is on the right. So that's why you are starting from the leftmost upper corner. But in this case, if the smaller department is on the left hand side and the non-adjacent side is here, then it means that you will start from the upper right corner. Okay? Then in a swipe pattern like ALDEP, what you will do is you will start placing K grids from here to the, for example, to down 1, 2, 3, 4, and etc. When you reach to the bottom of the box, then you move left and start placing K such squares. And when you finish with this, then you place the larger department to the remaining part. Okay? This is how Kraft places or exchanges two departments with non-adjacent, non-equal sizes. But of course, it has some problems that we will see later on. So, okay, this is an example. Let's assume that we want to exchange these two departments. This is the smaller department and this is the larger department. What do? We first draw a box in the boundary of these two departments, something like this. And then we remove the departments from here. And then we take the smaller one, which is this one, and go to the leftmost upper corner, which is this one. And starting from here, we start placing the departments, the squares. And how many? Since we have for this smaller one 8 squares, we will place 8 squares in a swipe pattern. So we start here and say that okay, this is 1 for the smaller department, this is the next one, then we move 1, okay, this is the third one, fourth one, fifth one, then we move right. But when we move right, you see there's one more grid on the right, so we start from the top and go through bottom, and when we finish with placing such 8, then the remaining squares are allocated for the larger department in the grid. By the way, there are different methods. In some cases it moves horizontally, swine pattern, and etc. So there may be some alternative methods to place these departments, but the basic idea is this. You remove the departments from the two departments from their current positions, take the smallest one and start placing the squares of the smaller department from the non-adjacent part of the box. Okay, let's consider a numerical example to understand this craft better. So in this example, we are given 8 departments. Okay, so their numbers, their names, receiving, milling, and etc. all given. And you can either represent these departments with such numbers, or if you like, you can represent them with letters as well. Okay, the area requirements of each of these departments are given. The flow between the departments are also given. So from, for example, department A, which is receiving, to department B, which is milling, the flow is 45. Okay, so the flow, total flow is given. There's one important thing that we need to decide on while starting with craft is, okay, so these are the area requirements, and we are going to represent these area with the unit squares. Then what should be the size of the unit square? If you assume that the size of a unit square, for example, this one, if you assume this to be 1 feet square, then in order to represent this 12,000 feet square, you need 12,000 such smaller squares. And for this one you need 8,000, for this one you need 6,000, and in total you will need maybe 50,000 or more such squares. And dealing with those many squares while exchanging these departments will consume a lot of time. Okay, so it means that considering one square to be 1 feet square is not suitable or manageable. So you can increase this size, and when you look at these area requirements, you see that all of them are multiples of 2000. It means that in fact you can represent one grid square, you can assume one grid square to represent 2000 feet square. And what happens in this case? You represent this department H with only 1 square. You represent this one with 6 squares, because 6 times 2000 is 12,000. You represent this with 4, and etc. You represent this with 3 squares. Okay, this is a small number of squares, and making the calculations will be easier. But on the other side, if you represent 2000 square with 2000 feet square of area with only one grid, one unit square, then the department shape will always be a square. Okay? You will never have L shape or different shapes. It will only be a single square, and it may not be realistic as well. So you need to determine the area requirements or the representation of this area with grids carefully. Not too many grids, not too small grids, but a manageable number of grids. And in this example, we decided to represent a area square to represent 400 feet square. Okay, 400 feet square. In this way, in order to represent this 2000, we require 5 grids. In order to represent 12,000, we need 30. Why? Because 30 times 400 makes 12,000. Okay, and when you add up these, so it's something around 100 and etc. Maybe around 150, and it's a manageable number, and it can provide you good results. Okay, that's why we decided to use 400. You may ask, can we use 500 because 500 also is a multiple or divider of these values? Yes, of course, you can use 500. And in that case, if you use 500, instead of representing this with 5 grids, you will represent with 4 grids. Okay. So can we use 100 instead of 400? Yes, if you use 100, then instead of 5, you will need 20 grids to represent this one. Okay, and the basic consideration here is this: it should be smaller enough so that the computer will not spend too much on making calculations. It should be large enough to provide you good departmental shapes, good granularity. Okay, that's the idea. So as we said, the Kraft algorithm starts with an initial layout. We identified the total number of grids for each department. Remember, department A was requiring 12,000, and with the grid representation, we said that it will require 30 grids. Okay, so when you look at this layout, it's 3 by 10. It covers 30 unit squares, 30 grids. Similarly, for each one of these departments, for department H, remember we required 5 grids, and in this shape we have 5 grids. Of course, what should be the width and the length of this initial layout? If it is given to you, then you need to use it. But if it is not given to you, then what you should do is you should add up the area requirements of all of these departments. 30 for A, 30 for G, 30 for F, 30 for D, and etc. Add up all these. And in total, for this example, we require 180 grids. Okay, 180. Then what do? You should divide this 180 to a rectangular area, so as much as closer to a square one maybe, or a good beautiful rectangular area, so that the length to width ratio is a good one. Okay, so for this example we divided this to 10 by 18. You could have used different ones. In some cases, okay, this number, total number of grids, may not be a multiple of two good numbers. So for example, in this case, it could have been something 179. Okay, what are the multiples of this 175 so that you are going to represent it as a rectangular shape? In this case, what you can do is you can increase this by 1 unit to have 180. Either you place a dummy department with 1 grid to do this, or you increase the size of one department with 1 grid initially. So instead of having 30 grids for A, you increase it to 31 grids. So in total you have, instead of 179, you have 180 grids. Then you divide this into 10 by 18, like this example, and find your initial layout and find your final layout. And at the end, when you come up with the result, you just delete one grid from department A, so that again it has 30 grids. Or if you use the dummy grid, then you just remove it from your layout, and at the end you end up with 179 grids. Okay, it can be done. Okay, so after this, we identified that we have 10 by 18 rectangle. The starting point for Kraft calculations is to determine the centroids. Okay. Of course, how did we come up with this initial layout? Initial layout can be found in different ways. For example, you can first run a construction algorithm like the ALDEP algorithm, and it provides you a layout. Then you can use that layout of the ALDEP algorithm as your initial layout of the Kraft algorithm, and you can try to improve it. This is one method. Another method is by yourself just create a feasible layout. Okay, you can do this by yourself, and this is how we come up with this initial layout. We created this layout by considering the grid requirements of each department. Okay, you can just randomly place them, or while placing these departments, you may consider the flows between the departments and try to make the departments which has closer relationship, higher flows, closer to each other. Okay, then the next step in Kraft calculations is to identify the centroids of the departments. And as I said previously, if the department has a rectangular shape like this one, then finding the centroid is trivial. It's easy because it should be in the midpoint of the length and it should be in the midpoint of the width. Okay, so the centroid of this rectangle is this point here. And you may assume that this corner over here, as in the coordinate system, to be 0, 0. Okay. You may assume that the size of each grid to be 1 unit. And then you can calculate the xy coordinate of each one of these centroids. Okay? So on the x coordinate, it is 1, 2, 3, 4, 5. Okay, x coordinate will be 5. And the y coordinate will be 1, 2, 3, 4, 5, 6, 7, 8, and 8.5. So this point is 5 and 8.5. And you need to do this for each one of those. But look, again, for B, we have a good rectangular shape. For C, we have a good rectangular shape. But for D, we don't have this rectangular shape, and we need to calculate its centroid. How can we do this? Of course, you can use different methods, but maybe an easier one is to divide this into rectangles and find the centroid of each of these rectangles, and then combine these rectangles and find their centroids. Okay, so for this example here, you may assume, for example, to divide it from here so that you have one rectangle on this side. Then for this side, you can divide it further from here, okay, so that we have one rectangle here and another rectangle here. Now you need to identify the rectangle, the centroid of each one of these rectangles. So for this one, the centroid should be here. For this one, the centroid should be here in just the mid of the horizontal and vertical distances, and for this one the rectangle should be here. Now we have three centroids, and I need to combine these three centroids, and of course this time in order to combine it, you need to consider the sizes of these rectangles. Okay, you can combine them in pairs. For example, I prefer first to combine these two. Okay, the centroid of these two should appear on this line connecting these centroids. Okay, and it should be, of course, closer to the one which has a higher, larger area. So it means that the centroid should be somewhere here. But where exactly? In order to understand it, you need to look at this proportion over here to the length over here. Okay, so the ratio of this length here to the ratio of this length here must be equal to the ratio of the smaller sized rectangle, the size of this smaller rectangle to the size of the larger rectangle. Okay, the size here is 3 squares, and the size here is 3 times 4, 12. Okay, so it means that 3 by 12 must be equal to this smaller length divided by larger length. And by using this, you can identify the centroid, the exact location of the centroid. Then combine this centroid with the other one. Okay, it means that the centroid of the total shape will be on this line segment. And again, the ratio of this part to this part will be equal to the size of this rectangle to size of this shape. And using that, again, you are going to calculate the coordinates of the final centroid. Okay, this is how you can do it. As I said, if the department shape is a little bit weird, then calculating the centroid by hand can be a little bit more complicated. But after you calculate these centroids, what you do is, since Kraft uses a distance-based cost computation, you need to find the rectilinear distances between these centroids of the departments and then multiply it by the flows between the departments, which is given in the table in the previous slide. Okay, so the rectilinear distance, for example, from this one to this one is this distance plus this distance. And as I said, if you calculate the coordinates of this centroid and coordinates of this centroid, the rectilinear distance will be the difference between x coordinates plus the difference between y coordinates. Okay, so when you calculate these rectilinear distances, you multiply them with the flows between the departments. And for this example, for this initial layout, we can calculate the initial cost to be 2,974 units. Now the next step in Kraft is to identify the exchange options. Okay, so as we said, Kraft may exchange two departments if they share a border or if they have the same size. Okay, A here requires an area of 30 grids and it's adjacent to B, C and G. It's not adjacent to E, remember? So if just the corner is touching to each other, it's not adjacent. They need to share a border. Okay, so whatever the size of A and B, we can exchange them. Again, we can exchange A and C and we can exchange A and G. But other than that, A requires 30 grids and D also requires 30 grids. So we can exchange A and D although they are not adjacent. Similarly, we can exchange A and F although they are not adjacent. And now you need to consider every possible exchange and estimate their effect on the cost. Okay, A and B, A and C, A and G, A and D, A and F, but you cannot exchange A and H because they are not sharing a border and they are not in the same size. Then you can exchange B and C, B and D, and nothing else. Then you can exchange C and D, C and E, C and F, and nothing else. Okay, you will consider all these exchanges and identify the exchange which minimizes the cost the most. In our example, exchanging departments E and F provides the maximum reduction in the cost. That's why departments E and F are exchanged. And how this exchange is done? So a border, a box around these two are placed. So initially remember F was here and E was here. And then we sketched a box around these departments. We removed them from their current position. We took the smallest department and go to the non-adjacent size upper left corner, and in a swipe pattern we placed the square grids, and to the remaining part we placed F. And you see the final layout after this exchange reduced to 2954. It was 2974. It reduced to 2953. Then with that layout, we consider all other exchange options again. And when we consider, we see that exchanging departments B and C provides the maximum benefit to the cost. And in this way, we exchange their positions. And you see that the final layout, this is the final layout after exchanging B and C, and the cost reduced to 2833.5. Okay, so this is the final layout, and then by making further exchanges you cannot reduce this one even further. This is the best that you can. But the thing is, this is a heuristic algorithm, and the final result depends on the initial layout that you provide to Cplex. It means that if you give a different layout, you may end up with a different final layout. When you have the final layout, of course, you can play with this layout manually to come up with a better design, better departmental shapes. Remember, if you look at the previous slide, so this department D, department H was here, and the shape of department D was something like this, and it had more corners. But what we can do is we can change this H, department H, from here to here. And remember, department H was requiring 5 grids, but here we have 4 grids. So in order to give the size of the required size to this H, we can move the border of H a little bit further so that these small areas, when you add them up, it will count up to 1 grid, and the total size of the department will be the same. And again, also, in order to satisfy the shape of department D, we can extend it a little bit or reduce it a little bit more. Similarly, for departments C and B, in order to reduce the number of corners and have good rectangular departmental shapes, we can move the borders inside the grids, not passing through the borders of the grids, but inside the grids, so that we will have good square or rectangular shapes. So these are the final adjustments, manual adjustments of the departments, and when you compare this layout with the previous one, this is more realistic and practical. We don't have too much corners. They are usually rectangular or L-shaped departments. We mentioned that if two departments are adjacent, or if two departments have the same size, then the Kraft makes an exchange. But having a shared border does not always satisfactory to find a feasible final layout. So consider this example and consider departments 2 and 4. You see the department 2 has such a shape in this layout, and department 4 has such a shape. And we want to exchange departments 2 and 4 because they share a common border. So how can we do this? Let's consider. So we remove these departments from this box over here. Okay. this sorry, this is the box. Okay, just remove the departments from this box, and starting from the smaller department, which is 4, go to the leftmost up corner, which should be this one. Okay, start placing 4. 1, 2, and 3. Okay, then the remaining ones should be allocated to 2. So this is 2, 2. But you see the others also will be 2. This one, and this one. But when you look at the department 2 here, it's not connected. Okay, department 2 has some area here and has some area here, and it's not connected. And it means that it's this final layout, final shape is not feasible. Okay, you can assume that why did you start 4 from this side in order to obtain a feasible schedule? We could have started from here. Okay, let's place 4 to here. 4, another 4, another 4. And again, you see the remaining space for 2 is disconnected. So wherever you start for this department 4, it always divides the area into 2 disconnected parts. Even if you start from here, 4, okay, 4 and 4, the remaining area for 2 is disconnected. So it means that sharing a same border does not always means that you will end up with a feasible layout after the exchange. So if we summarize the Kraft algorithm, it is a so-called path-oriented method, which means that the final layout that you will obtain will be depend on your initial layout. Okay? So in order to get a better final layout, you may try different initial layouts. You may start with different initial layouts, and you may end up with different final layouts, and you can compare these final layouts with each other and select the best one. It's possible. Kraft can be said to be flexible with respect to department shapes. So, for example, in pairwise exchange, it always works with the same size departments, and the department shapes never change. But here, depending on the pattern that you fill in, the department shapes will be changed. But at the end of this, you may have departments with irregular shapes. Okay? For this purpose, in order to obtain a realistic and practical departments, at the end of the algorithm, you may need to make some makeup or finishing to provide better designs. Another version of Kraft, maybe you can call it an improvement or adjusted algorithm, is the MCCraft or MCCraft. It's an implementation of the Kraft algorithm in personal computers. It's also it's an improvement algorithm and takes an initial layout and tries to improve it. But the main difference of MCCraft from Kraft is in MCCraft, you can exchange any departments with each other. So in Kraft, you can only exchange 2 departments if they share a border or if they have the same size. But in MCCraft, these conditions need not be satisfied. Even if in that case, you can exchange these departments. Okay, and in such a case, if you exchange 2 departments which are not sharing a border and which are not in the same size, the MCCraft automatically shifts the other departments with respect to this exchange. In some sense, this MCCraft's method is similar to the ALDEP. It divides the facility into bands, like in ALDEP, and you represent the total layout with a number of bands, and these number of bands are specified by the user. Okay? And in order to place the departments into this layout, we use a horizontal sweep pattern. In ALDEP, we were using vertical like this, but in MCCraft, we will be using a horizontal pattern to place these departments. Okay. And the layout is specified by a sequence of the departments. Okay, when the sequence of the departments is given, then you will find a layout corresponding to that sequence, and it means that an exchange in MCCraft is in fact an exchange in the sequence of the departments, not in the layout itself. The layout is a result of the sequence. When I say the sequence of departments, for example, it's something like this. I say department 2, department 5, 1, and 3, and etc. So this sequence tells us or shows us in which sequence these departments will be placed in this layout using this sweep pattern. Okay, so when I give you first place this 2, you start with 2, placing with 2, and then when you place required number of grids for 2, then you move to 5. Do the same thing for 5, then you move to 1. Okay, so if I exchange two departments, let's say I exchange 5 and 3, then it means that your sequence is 2, 3, 1, and 5. And what does it mean? Again, in order to place these departments, you start with 2, then you continue with 3, then move to 1, and then move to 5. Okay? So we will make an example on this. In order to run this MCCraft, it requires the dimensions of the facility in terms of length and width from the user, and it requires the number of bands again from the user. Okay, and for example, if the number of bands is 3, it means that it divides this width into 3 bands, so that you start from the top band here. You start placing the departments to this top band, then you move to the bottom one, and then you move to the last one. Okay, so the first step of the MCCraft algorithm is to obtain the length and width of the layout and the number of bands. In the second step, you can input the initial layout as a layout vector. So you can give exactly the layout to MCCraft if you like, or you can just give the sequence of departments. Like in the previous example, I told you 2, 5. You give this sequence, and it finds the corresponding layout to this sequence. Okay, and then in the third step, this Kraft algorithm implements this exchange. Sometimes it's called swap, the same thing, swap exchange operations. Okay, and this is not limited to the equal size or adjacent departments. It can swap or exchange any department. If any of these exchanges improves the cost, then the two departments are swapped, like in the Kraft algorithm. Otherwise, the algorithm stops. Okay. So if there's an improvement, you repeat step 3 and 4 again and again until you find a layout in which there are no further improvements. So okay, let's consider the previous example, the same example, and try to solve it with MCCraft. But here we represent each one of the departments with even smaller grids. Okay. So we provide the width and length of the layout, and we also provide the number of bands. So the number of bands in this example is given as 3. Okay, we need to give the initial layout, and the initial layout, as we said, if you like, you can give this one as it is, write just 1, 1, 1, and etc. Or you can give the sequence of the departments. So 1753, in this case, the sequence of the departments is given. When you give this, the MCCraft finds the corresponding layout in this way. Okay, for 1, how many grids I need for 1 to represent 1? So it knows it. Then starts placing 1 to this first band. Whenever it places the necessary numbers, then it moves to the next department, which is 7. So it continues with 7, placing the grids, and when it's finished with 7, it moves to the next one, which is 5, then moves to the next one, which is 3, moves to the next one, which is 2, then to 4. You see 4 is not finished until the end of the band, so it continued, okay, with the next one, and etc. So this is the final layout. This is the initial layout effect corresponding to this sequence. Then all pairwise exchange options are considered. Okay, so, and as I said, the pairwise exchange options are considered not on the layout but on the sequence. So initial sequence, for example, was 1, 7, 5, 3, and etc. It was going in this way. So it considers exchanging 1 and 3, 1 and 5. 1 and 5 are not sharing a border, and they are not in the same size. But even if that's the case, you can still exchange, because what happens after you make this exchange, MCCraft takes this sequence and starts placing the department on this layout according to this adjusted or exchange sequence. Okay, so it finds a new layout corresponding to this new sequence, and this is the final layout that we obtain for the example. So in this case, the MCCraft exchanged departments 3 and 5 first, then 3 and 8, and 3 and 4, and 2 and 3. And the final layout or final sequence appeared to be this one. And the layout corresponding to this sequence is first place 1s, then place 7s, then 8, then 5 and 3 and 2. And you see for this department 2, it's a very weird shape and it's not a good shape. Maybe it's better to make a manual adjustment at the end to this 2, so that you leave this space to department 4, but you move this border a little bit down so that you have a rectangular shape for 2 and a good shape for department 4. Okay, what can we say about MCCraft? What can be some of its disadvantages? For example, it divides the departments into bands. Okay, the user satisfies the bands, but your initial layout, if you are currently using a layout, that layout may not fit to these bands. Okay, so you may not be able to put your initial working layout into this MCCraft. It's one disadvantage. If you have some fixed departments, okay, as we said previously, in Kraft you may have fixed departments to indicate elevators and etc. If you have such fixed departments, then it may cause problems, because in the layout those fixed departments position should not be changed. But here, when you adjust the sequence of the departments, you may end up with infeasible solutions. The shape of the facility is a restriction for MCCraft. But you see the results in MCCraft are smoother. The shapes of the departments in MCCraft are smoother when we compare with Kraft. It's more like rectangular shapes due to this dividing the layout into bands. There are more exchange alternatives, because in Kraft the exchange is only limited to the departments with same sizes or departments sharing a border, but in MCCraft you can exchange any departments, so there's a possibility to create better solutions, but it also increases the number of alternatives to evaluate, and it may take a lot of time. And also MCCraft may allow for multi-floor planning. Okay, so these are the Kraft and MCCraft algorithms, and this is the last lecture that we will have on layout design. Okay, so you will have some self-study questions on this video lecture.